Here we go. And we'll play this video. Enjoy your video.
In the 1920s, the German mathematician David Hilbert devised a famous thought experiment.
Can you guys hear the sound? Yeah, okay, cool, nice. Let's watch this.
To show us just how hard it is to wrap our minds around the concept of infinity. Imagine a hotel with an infinite number of rooms and a very hard-working night manager. One night, the infinite hotel is completely full, totally booked up with an infinite number of guests. A man walks into the hotel and asks for a room. Rather than turn him down, the night manager decides to make room for him. How? Easy. He asks the guest in room number 1 to move to room 2, the guest in room 2 to move to room 3, and so on. Every guest moves from room number n to room number n plus 1. Since there are an infinite number of rooms, there is a new room for each existing guest. This leaves room 1 open for the new customer. The process can be repeated for any finite number of new guests. If, say, a tour bus unloads 40 new people looking for rooms, then every existing guest just moves from room number n to room number n plus 40, thus opening up the first 40 rooms. But now, an infinitely large bus with a countably infinite number of passengers pulls up to rent rooms. Countably infinite is the key. Now, the infinite bus of infinite passengers perplexes the night manager at first, but he realizes there's a way to place each new person. He asks the guest in room 1 to move to room 2. He then asks the guest in room 2 to move to room 4, the guest in room 3 to move to room 6, and so on. Each current guest moves from room number n to room number 2n, filling up only the infinite even-numbered rooms. By doing this, he has now emptied all of the infinitely many odd-numbered rooms, which are then taken by the people filing off the infinite bus. Everyone's happy, and the hotel's business is booming more than ever. Well, actually, it is booming exactly the same amount as ever, banking an infinite number of dollars a night. Word spreads about this incredible hotel. People pour in from far and wide. One night, the unthinkable happens. The night manager looks outside and sees an infinite line of infinitely large buses, each with a countably infinite number of passengers. What can he do? If he cannot find rooms for them, the hotel will lose out on an infinite amount of money, and he will surely lose his job. Luckily, he remembers that around the year 300 BCE, Euclid proved that there is an infinite quantity of prime numbers. So to accomplish this seemingly impossible task of finding infinite beds for infinite buses of infinite weary travelers, the night manager assigns every current guest to the first prime number, 2, raised to the power of their current room number. So the current occupant of room number 7 goes to room number 2 to the 7th power, which is room 128. The night manager then takes the people on the first of the infinite buses and assigns them to the room number of the next prime, 3, raised to the power of their seat number on the bus. So the person in seat number 7 on the first bus goes to room number 3 to the 7th power, or room number 2187. This continues for all of the first bus. The passengers on the second bus are assigned powers of the next prime, 5. The following bus, powers of 7. Each bus follows powers of 11, powers of 13, powers of 17, etc. Since each of these numbers only has 1 and the natural number powers of their prime number base as factors, there are no overlapping room numbers. All the bus's passengers fan out into rooms using unique room assignment schemes based on unique prime numbers. In this way, the night manager can accommodate every passenger on every bus, although there will be many rooms that go unfilled, like room 6, since 6 is not a power of any prime number. Luckily, his bosses weren't very good in math, so his job is safe. The night manager's strategies are only possible because while the infinite hotel is certainly a logistical nightmare, it only deals with the lowest level of infinity, namely the countable infinity of the natural numbers, 1, 2, 3, 4, and so on. Georg Cantor called this level of infinity Aleph 0. We use natural numbers for the room numbers as well as the seat numbers on the buses. If we were dealing with higher orders of infinity, such as that of the real numbers, these structured strategies would no longer be possible, as we have no way to systematically include every number. The real number infinite hotel has negative number rooms in the basement, fractional rooms, so the guy in room 1/2 always suspects he has less room than the guy in room 1, square root rooms like room radical 2, and room pi, where the guests expect free dessert. What self-respecting night manager would ever want to work there, even for an infinite salary? But over at Hilbert's Infinite Hotel, where there's never any vacancy and always room for more, the scenarios faced by the ever-diligent and maybe too hospitable night manager serve to remind us of just how hard it is for our relatively finite minds to grasp a concept as large as infinity. Maybe you can help tackle these problems after a good night's sleep, but honestly, we might need you to change rooms at 2 a.m.
Okay, that's it. That's the end of this great video. I love this video. Explain you how we have different types of infinity. Why is it still playing? Absolutely. Cool. Let me share my screen first. Absolutely. So this video shows you different types of infinity. We have what he's mentioned, L(0). L(0) is for the cardinality of natural numbers, and all the other sets that has the same cardinality with natural numbers. And then what is bigger, even bigger than this infinity? We know that we have infinitely many natural numbers. What is even bigger than that? We have the cardinality of real numbers. It's called C. The cardinality of real number is called C, which is not covered in this course, but it's quite interesting that we have infinitely many real numbers, but this infinity is actually bigger than the infinity for the cardinality of natural numbers. It's actually exactly 2 to the power of L(0), which is 2 to the power of the cardinality of natural number equals to the cardinality of real number, which you will also not notice in 102, but it's really interesting. And you can even have bigger infinity, which is even bigger than real number, and you can even have bigger and bigger and bigger and so on. Okay, so this part is really interesting. We will not go there. We will not move on to countable or uncountable or just finite sets yet. That's going to be next. This number is wrong. It's not tutorial 8. It's tutorial 9, isn't it? Yeah, it's tutorial 9. Do not know why I put 8 here, but it's wrong. This is wrong. It should be 9. Just bothers me because I feel like I have more class to teach. What do you love? Anyway, how do you guys feel about cardinality? Fun? Interesting? Isn't it fun? I think it's really fun. Cantor's diagonalization was hard to get. Seriously? It's one of my favorite proof actually. Cantor's diagonalization, one of my favorite proof. I love to talk about it. We're not going to talk about it today. We'll talk about it next week. We'll talk about Cantor's diagonalization argument next week. Cantor is a great mathematician. I think I mentioned it a long time ago about Cantor. When he came up with this whole we have different types of infinity, he was struggling in severe mental disease. Basically he was on a lot of drugs because he had really bad mental disease. Yeah, that's why we always say there's no way you can come up with this without drugs. Again, don't get me wrong, I'm not saying you should take drugs. It's just how amazing he came up with this like a few hundred years ago. when he just came up with this, nobody believed him. He sent his papers to a few really famous mathematicians at that time, and they all just threw out his paper in garbage bin because nobody believed him. They did not recognize this until, so the whole thing, the whole set theory thing, nobody trusts him because it was like everyone was like, this is bullshit, how can we have different types of infinity? Until another mathematician also showed that, so they also came up with this, and they finally went back to this. They were like, oh, so it's actually, so it was like mind-blowing, not just for you, it is mind-blowing for many famous mathematicians. So if you don't get it, that's okay. Okay, so even famous mathematician at the beginning, they did not trust him. You're smoking. So yeah, so it's okay if you don't get it at the first. I personally find it fascinating. It is mind-blowing for me. It is one of the reasons I decided to switch to math major. Yeah, so I think I mentioned them many times. Cardinality and fields are my favorite part of this course. They are part of the reason I switched to math major when I was in undergrad. I love them. Anyway, let's talk about function composition first, the boring part first, and then we will talk about the fun part. So function composition. I don't even know what to say. I do not like talk about this, but we do have to talk about this. Where do I even start? We will start with, I don't know. So let's start with a definition. Hold on, let me find my stuff. Can't find anything. Interesting. Okay, so function composition. What does it mean? Did I share my screen? I did, right? Can you see? Let me see. Okay, cool. Tutorial 9. Cool. So proposition of composite function. I hope you know what's function composition already, because well, this is also covered in calculus. So the composition of two injection is an injection, clearly. Yeah. The composition of two surjections is a surjection. The composition of two bijections is a bijection. So you can use them because, well, they were proved in your course notes. Actually, only one of them were proved in your course note, but you can use them. Unless the question is asking you to prove them, then you cannot use them anymore. Number 4, if f is from A to B and g is from B to C, there are two bijections, then the composition inverse equals 2, so you need to switch the order, which is pretty clear. You should also know that if a function is bijective, then it has inverse, and then the inverse is also bijective. Pretty straightforward stuff. I do not have time to cover everything, so we'll do we'll do some of the questions. We'll do example 1. So let's look at example 1. Hopefully this is straightforward for you. I want to quickly finish this and go to cardinality, so quickly finish this. If f is a bijection and it's from A to B, g is from B to A, it's a function. So they didn't tell you g is bijective, they just tell you it's a function and it's from B to A, such that f compose g compose f of A equals to f of A for all A in A. Now they want you to prove that z equals to f inverse. Okay, before we do this, I want to recall, if they want you to prove two functions are equal, so what do we need? So to for two functions. So for f equals to g. Okay, what do you need? Okay, it's not something, I should say, it's something people would make mistakes. Okay, because you need three conditions. One, you need f and g have the same domain. Two, they need to have the same codomain. Three, for all, so let's say they have the same domain. Let's call the domain A, codomain B. So for all A in the domain A, f of A should equals to g of A. So if you want to prove two functions are equal, you need to show all three things. Yes, I know this question is for inverse. I'm talking about generally if you prove two functions are equal. Okay, so this is what you need to do if you want to prove two functions are equal. Generally speaking, missing one, you will lose mark. Okay, you will definitely lose mark if you don't mention them, because you need all three conditions to satisfy in order to say they are equal. Cool. So now let's look at this question. For this question, you want to prove G equals to F inverse. So first of all, do they have the same domain? Do they have the same domain? Yes. Okay. So let's say, first of all, you should say F inverse exists, because sometimes it does not exist, since F is a bijection. And F inverse is from B to A. So we know, so F inverse and G have the same domain and codomain. So what do we need to show? So we just need to show that for all B in B, because B is your domain, G of B equals to F inverse of B. So this is what we want to show now. Okay, so this is what we want to show. So we want to show G of B equals to F inverse of B for all B in B. Now, anyone has any idea of where to start? The only thing that's given to you is this, basically. You know this. What else do you know? You know that F inverse. So you know that F inverse F of X equals to X. You also know this. You can take inverse on both sides. Yes, you can do that. So let's do which inverse? F inverse, right? Okay, so let's apply F inverse on both sides. Make sure you are using the same direction. So if you apply on both sides on the left, you need to do both sides on left. Or if you want to do it on the right, then both sides need to be on the right. So we have F inverse F G F of A equals to F inverse F of A. What does this give you? What do we have from here? A on the left-hand side, yeah. What about right-hand side? No, A is not on the left-hand side, it's on the right-hand side. So this side we have A. That's correct. What about left-hand side? G compose F of A, exactly. So we have G compose F of A. But what do I do next? What do I do next? Remember, this A is in A. So A is in A, so it's not B, okay? It's not in B. A is in your codomain. What do we do? You cannot apply, well, you don't have inverse of G. G is not necessarily a bijective. How do you apply B? Can we use F inverse F equals to X? Yeah, you can use it, but how do I use it? Again, guys, think about this. This is A, so this is A. A is in what? A is in your codomain. Okay? So you want domain. So A is in your image. A is in your image. It's not F of A equals to B. F of A is not F of A equals to B. Oh, it is F of A equals to B. Sorry. I was wrong. F of A equals to B. That's correct. That's a correct direction. Go from there. F of A equals to B. And what does that mean? Also, why do we have F of A equals to B? You need to explain those. So let's pick one element from B. So let's let B in B. Then what do I do? First of all, why do we have F of A equals to B? Because F is what? Bijection, okay? Since F is bijective, which means it's definitely surjective. In particular, it's surjective. That means we know that there exists A in A such that F of A equals to B, right? And then by definition of inverse, we know that F inverse of B equals to A. Then what do we do? Now I have B. I have B, I have A. I can just substitute this back into this equation. So let's call it star. Now substitute sub into star. We get G compose F of A is F inverse of B equals to F inverse of B. Right? So what does this tell you? What's on my left hand side? G of B. So G of B equals to F inverse of B. And we're done. That's what we need to prove. Question? I'm so hungry. My hand is shaking now. Do we have question? Is this clear? I think it's pretty clear. Can we use F inverse F equals? What do you mean can we use that? How do you want to use that? We basically used it. We used it here. Yeah. Well, Lance, you can use that, but that can only give you A. But A is in your codomain. You want B, you don't want A. So that doesn't tell you anything. Because A is in your codomain, but you want your input to be from domain. Yeah, so that's the key because A is not from B, A is from A. Cool. We'll skip the next one because we don't have enough time. So I'll do this one in my next tutorial, which will be recorded. Let's talk about cardinality. Okay, cardinality. Two sets, A and B, are said to have the same cardinality if there is a bijection between them. That means what? That means whenever they ask you to prove two sets have the same cardinality, you need to construct a bijection between them. And then you need to show that the function you come up with is indeed a bijection. So here, let's write it down. Sorry, my hands are shaking, so it's hard for me to write now. To show the cardinality of A equals to the cardinality of B, you need to construct F goes from A to B or B to A, doesn't really matter. Whichever way you find easier, you use it. From A to B, my jacket over your keys. Okay, back to this. You need to construct the function goes from A to B or B to A, and then prove your F is bijective. Is a bijection. So based on this, you should know that I don't have food yet. Based on this, you should know that the easier your F is, the easier it is for you because you need to prove it's a bijection. If you come up with a really, really complicated function, then you're making your life really hard. Does that make sense? Because I know you guys do not like proving a function is bijective. If you come up with something that's really complicated, then you're making your life really hard. So you should always use something easy. So you should always use something that's easy to prove it's a bijective function. Okay. Let's do some examples. So which one do you want to do, A or B? You want to do A? I thought you want to do B because B looks harder. Wait, we're not gonna do A, B. A is definitely much easier. Okay, let's try again. Start from now, A or B. Okay, let's do B then. B is actually harder. So, B. They want you to show the set of integers which are divisible by 3 and the set of even positive integers. They have the same cardinality. how do we come up with a function? So what I usually do is I do some rough work first. So let me use another color for rough work. So rough work. Here is my rough work. What are the set of integers that are divisible by 3? Yeah, list out the sets. Exactly. So a set of integers. Oh, my hand is shaking so hard. Set of integers which are divisible by 3. What are those? This looks really taking too much space. So we would have what? What are the set of integers divisible by 3? Come on, list them out. Just 3, 9, 12? Anything else? Do we start with 3? I don't think that's a good idea. Which one should we start with when you list them out? You should list them out in certain pattern so that it's easy to follow. So whenever you talk about it, people know, oh, you're talking about like we know that, oh, the 10th one will be what. So I suggest we start with 0. So we have 0, we have -3, we have 3, we have -6, we have 6, -9, 9, and so on. If I list it in this way, I know that, well, if you ask me what's the 20th one, I know exactly which one we're talking about, right? So let's do it in this way. What are the set of even positive integers? Which one do we start with? Even, positive, even, positive, positive. Okay, 2, we start with 2, right? So it's 2, 4, 6, 8, 10, 12, 14, and so on. Now, what I want to do is I want to map 0 to 2, -3 to 4, 3 to 6, and so on. So I want to do this mapping, right? Remember, this is what we want to do. And if I observe that, I see that those are alternating from positive and negative values. So I'm going to deal with the positive ones first. So let's only look at the positive ones and come up with our function. So here is my rough work. So I want to map from 0 to 2. What does that mean? Yes, you can use piecewise function. You can use any function you want as long as it's bijective. But you need to prove it's bijective though, okay? So keep in mind, you need to prove it. So 0 to 2 looks like it's just +2. So let's just write it here. If I use the same method, is it just 3 + 2? But 3 + 2 is not 6 though. So I want 4 + 2 instead, right? But I started with 3. How do I go from 3 to 4? What do I need to do to go from 3 to 4? X + 1, just +1. Okay, let's say this is one of the possibility. So let's say X + 1 to get this, and then +2. But this doesn't work for this one though, because if you do 0 + 1 and then +2, that map to 3. It's not 2 anymore. So this is not the function we're looking for. How else can you map from 3 to 4? Divide by 3 and multiply. No, wait. Times 4 over 3. Yes, exactly. So another suggestion is we use 3 divide by 3 and multiply by 4. In this case, you can get 4 and then plus 1, plus 2. This looks like it works. Let's go back and check if 0 works. So we use 0 divided by 3 times 4. That's still 0 plus 2. Seems like this one worked for now. Check the next one. 6 divide by 3 times 4. That's 8 plus 2. That's 10. Looks like this one works too, right? And if you continue, you'll see that everything works. So that's my first function. So my first 1x is greater than or equal to 0. I'm gonna use x over 3 times 4 plus 2. Okay, does it make sense how we came up with the function? Okay, now let's look at the negative part. So let's look at those parts. I have -3 mapped to 4. Well, first of all, it's negative number mapped to a positive number. Then what do we do? What do we do to keep it a positive number? Well, you don't want absolute value, right? Because absolute value, when you prove it's bijective, that's hard. So you don't want absolute value. Times -1, exactly. So I'm gonna multiply by -1. So negative of -3. Okay, so this would be 3. How do I make it 4? I wanted to map to 4. Yes, you do this again. Okay, you do this again. So you wanna divide by 3 and then multiply by 4 again. So that's our suggestion. Let's look at the next one. Negative of -6. Let's divide by 3 times 4. Does it work? Is it 8? Yes, right, it is 8. So this is good. What about the next one? Negative of -9 over 3 times 4. It's 3 times 4, so it's 12. This is good as well. So my suggestion is 1x is less than 0. We use -x over 3 times 4. So that's my function. I have a piecewise function. So we can write our proof now. Let's see. This is B. Actually, I'll use this color, B. Let's use yellow to write my whole proof. So proof let's let 3z represent the set of integers which are divisible by 3, and let's say 2n, because it's natural number, represent, because it's a positive even number, the set of positive even integers. And define the function, define f. F is gonna go from 3z to 2n by, so here is my function, f of x equals to, so it's 4x over 3 plus 2 if x is greater than or equal to 0. and it's negative 4x over 3 if x is less than 0. So this is my function, but how I also need to prove it's a bijective function. So let's prove the injectivity first. How do we show it's injective? F of A equals to F of B, okay? So suppose A, B are in 3Z and F of A equals to F of B. But what do we do next? We do need to take cases, but how do we split our cases? How exactly do we split our cases? Because look at this, guys. This is going to be positive. This is also going to be positive. So you cannot do positive negative split cases. Then how do you split it? That's like a tricky part here. Negative, negative. Well, you only know f of a, b. You cannot restrict your a and b. You can only restrict your f of a and f of b. We don't know anything about a and b yet. So what do we do? What are my cases? I suggest you, is it not a b greater than or equal to 0? It's not, because you don't know a and b. You only know f of a and f of b. So you can only talk about when f of a, f of b, something, something. So go back to this, guys. You should go back to this and see how we split the cases based on this row. So one case is 2, 6, 10, 14, and so on. The other case is 4, 8, 12, and so on. So how do we split it? Do you see a pattern here? Exactly. If it's divisible by 4, right? Do you see? This one is always divisible by 4. So that's our cases. One case is when it's divisible by 4. The other case is when it's not divisible by 4. Does that make sense how we came up with this? So you want to go back to your output and see how it works. Yeah, you're looking at this because now you only know f of a, f of b. So you're looking at your codomain, okay? So my first case is when they are divisible by 4 or not divisible by 4. Let's say not divisible by 4. Case 1. If f of a and f of b are not divisible by 4, then what do we have? Then you would have the first case, right? You would have this. So you would have 4a over 3 plus 2 equals to 4b over 3 plus 2. So 4a over 3 equals to 4b over 3. So a equals to b. I should write more steps because some TAs are really harsh on this. I should not skip steps. Sorry, I'm a bad example. Okay. So for this case, we show that they're injective. Okay. Second case, if f of a and f of b r divisible by 4. Then what do you have? Yeah, I know some TAs are really harsh on this. So I'll try not to skip any steps, okay? I think it's pretty obvious, to be honest, like going from here to here, pretty obvious, but again, there is no obvious steps in 102, so let's not skip anything. So this one will give you negative 4a over 3 equals to negative 4b over 3. Okay, do not skip steps. Okay, so this is gonna be negative 4a equals to negative 4b, so a equals to b. Okay, so in both cases, we have f of a equals to f of b implies a equals to b, and so f is injective. Now you need to prove surjectivity. Okay, so surjectivity. How do we prove surjectivity? Surjective. I'm gonna pick, so that y belong to 2n because this is my codomain. And now what do we do? How do we prove it's surjective? Yeah, but how do I do that? Seems like I taught you guys well. You know exactly what to do. Pretty nice. But how do we do that? How exactly do we do that? We did that already. Here, we have this already. What is my x? That's my question. Solve for x. Yeah, that's what I'm asking. Now solve for x, guys. Do the work. Well, you need to discuss cases again, right? So the first case is one if y is not divisible by 4. Then what do we take? Take x equals to what? Someone solve it and tell me. This is not divisible by 4, not divisible by 4, not divisible by 4. So it's a first case, this one. Why do you guys have different answer? Okay, 3 times y minus 2 over 4, 3y minus 6 over 4, they are the same thing, okay? So suppose you're right. I didn't do it, so I don't know. Let's try. Since 2 of you got the same answer, let's suppose it's correct. Is this divisible by 3? Is this, I'm asking if this is divisible by 3. Yes, why? Amber alert. Did you get Amber alert? I got Amber alert. Oh, this is a test. Okay. Okay, fine. This is divisible by 3 because you need to explain this, okay? Since what's y? Y is a, what is y, guys? y is this. So y is this. -2. -2 times 3. So it's divisible by 3. I'm just gonna leave it. Since y, let me think how do I rephrase it? Since y is in what? Y is a positive even number, integer, and it's not divisible by 4. Why is it divisible by 3? Why is 4 divides y minus 2? So basically, I'm asking you, why is this integer? Because y is even natural number, not divisible by 4. So you can write y as 4k plus 2. Okay, because it's even integer, not divisible by 4. So -2 over 4 is just gonna be k. That's gonna take a while to write it down. Since y is even natural, not divisible by 4. So y can be written as 4k minus plus 2. So k is a natural number. Shall I write it as -2? Yeah, I should write it as -2. Oh, I can write it as natural union 0. That will be good. So y -2, 3, 4. This will be 3 times 4k minus 2. Oh, plus 2, I meant. Plus 2 minus 2 over 4 is 3k. Okay, so it must be in 3 then. Okay, so now you can plug it back in. So f of 3 times y minus 2 over 4 equals to 4 times 3 y minus 2 over 4 so over 3 plus 2 equals to 3 y minus 2 over 3, because those canceled out, this canceled out. Okay, plus 2, so equals to y minus 2 plus 2 equals to y. And second case, if y is divisible by 4, then what do we take for x? Take x equals to what? What is my x now? -3y over 4, that's correct. So take it as -3y over 4. This is in 3z. Why? Because y is divisible by 4. Okay, so my f of negative 3y over 4 equals to negative 4 times 3y, negative over 4 over 3. So that's canceled out. So that's 3y over 3 equals to y. Right? So in both cases, there exists x in 3z such that f of x equals to y. So f is surjective. Done, this question is done. Long question, huh? How do you feel? Good? Done. Pretty long. Took us 2 pages. Satisfied? Isn't that sentence statement repetitive? Do we need to write that? What's repetitive? You mean this? Are you talking about this? Well, okay, let's say personally, I don't even think you need to explain this, but I know if you do not, you will lose mark if certain TAs are marking. So to save me from remarking, do you know how many remarks I get for the term test? More than 10%. More than 10% of 102 students requested remark. It was a help for me. So to save me from going over remarking, I suggest you to write it even though it's kind of repetitive. Okay. We'll stop here. The rest of the question, I'll do them in my next tutorial, which will be recorded as well, so you don't need to show about it. Yeah, so you don't need to attend another tutorial. You can just watch the next one. I mean, watch the recording, 2 times speed or something. But I'm gonna stop here because I wanna have a bite of my lunch before I go to my next tutorial. So you guys should leave now so that I can eat. Bye.